So in this lecture, we are just going to discuss about some regression technique. Till now, we have seen that we are using our SVM model by simple classifications, by simple doing the job of classifications. But here we are simple just doing some simple modifications. We are using the SVM to regressions. So in regression technique, we are calling the SVR, support vector regressors. So our classifications we are simply calling the SVM, simply support vectors machine. But for regression technique we are calling this the support vector regressor, simply SVR. For this it is SVR, support vector regressors. So we see that for some SVM classification, we see that for SVM classification, another language if we call the SVC, support vector classifier. So what will be our yi value here? So we see that our yi lies between +1 and -1. If it is positive class, then +1. If it is a negative class, then it is -1. But in support vectors regressor, what will be the value of r? What will be the value of this r? This r is lies this this yi. So support vector regressors, the yi lies in the real number. Okay. So just first doing the some mathematical portions of it. How the mathematics? Just see the mathematics of it. So what we'll see, we have to minimize we have to want to maximize the margin distance. In another language, just taking the inverse functions of the margin. So our objective functions was, that is 1/2 norm of w. We see that 2 by norm of w is our actually the margin. Just we are taking the inverse. Just we are is by simply we are using this function as regularizer term. Okay. So first just write down the optimization problem. Then I am discussing it. And we have some such that we are here introducing our constants be like that. Yi minus w transpose xi plus b less than epsilon, and as well w transpose xi plus b minus yi less than equals to epsilon. So for all I, it will happen. Just I am going to discuss everything step. Just be patient with me. First write down the equations of the regression. Simple. This is 1 hour. This is 1 hour linear functions of SVM. Simple. This is the linear SVR technique, linear regression technique. Linear SVR means linear technique. This one, simply that linear technique. So just see this here. Actually, here in this formulation, this one is your actual hyperparameter. We have to just why we call this one is the hyperparameter. We have seen step by step. This is simple our hyperparameter, and this thing is our simple our regularizer term. Okay, these are the things here we are using. Now just see the interpretations of this. Now just see this step by step interpretations of. So what will your query function? Just if you remember, we are finding our query point, the output of the query point from this function. Just if you remember, by simple classification technique, we are finding our query point by simple w transpose xi plus b. If this one is the greater than 0, then our classifier doing job greatly will properly classified our data points. If it is less than 0, then it is incorrect, misclassified. Okay. So similarly here it is our query functions. From here we are finding this query function. Okay, but here it is actually we are getting a real number here. So that we call here yi hat. Yi hat. But here just I am comparing. For classification, we are taking this value as sign. If it is greater than is equals to 0, then considering the correctly classified. If it is less than 0, then we are considering misclassified. But in regressions, we are not taking this kind of situation. We are just taking its value, and we have just taking this is our approximate value of our yi's. Just if you just put down the query point here, then it will be the output of our model output. Okay, it is not the original output. So what is the original output of our model? Our, for suppose let's take, we have a data set, let's take xi yi. So yi is the original output, and this I is the output from our model. Okay, so now the error will be what? So the error will be, your error will be yi minus yi hat. This thing is actually the error. So just see this equation now. Just I am writing this thing in here. Just instead of this one, I am writing yi hat. This thing or this thing both same. Just I am using this one, and as well once using this thing. If you just taking two things, these two equations, this is actually the error equation. This is our original output of our model, or original output value of a data set, and this is the output of a data set from our model. Okay, this is the approximate output, this is the original output. The difference of these two between is also will be less than our error value. So just I am taking these equations here. So because of this, we are calling this because of simple this reason, we are calling epsilon is our hyperparameter. According to our requirement, we have to choose this value, how much we are interested to reduce the error. Because of this, because only for this reason, we are calling this equation a hyperparameter. I think now this concept is clear why we are calling. And simply we are also see that in if you just revisit the loss minimization functions, how the interpretations of the loss functions, how to calculate the SVM equations from our loss functions, then there we are this term we are considering as a regularizer term. Okay, now I am not repeating this thing again. Just if you revisit, if you just forget, please revisit this lecture, you can easily find from there. Okay, so now let's draw a function. Suppose our data set was like this. Suppose our data set was like, if you see, and here our data set was like this. Okay, just see this situation. In these situations, our data set will be properly linearly separable, almost, not properly, almost it is linearly regression. If you just approximate one line from this data point, so the base approximations will be here. This one will be the best approximation. So simple, if we just using this technique, we can easily separate. Just we are using this formula, this mathematical objective, these mathematical equations. If we are using for this data set, then we can easily find this line. So because it is a linear SVR, you can use a linear SVR. But if you just see the best regression line of this set of data points will be is this one. This one will be the best regression line from for this data point. Just see this. So here we have not used directly this mathematical equation. Here as well we have to use the kernel concept that we discussed in previous lectures. Okay, simple, here we have to use the kernel SVR. Okay, kernel SVR, and as well we have to choose our epsilon hyperparameter properly. Okay, so totally this for nonlinear regressor, this situations are depend on two things: how you choose the proper kernel and how to choose your hyperparameter. This depends on these two things, how you make your model appropriately. Okay, but linear regressions we don't have to choose such kind of thing. It is so easy, but for non-linear we have to choose. Just we see in previous lecture this kind of thing. Okay, now just I am now just I'm now, before concluding this lecture, I am just discussing how the hyperparameter behaves. Okay, for the trade-off between high just overfit model and underfit model. That is one kind of bias to handle the bias variant trade-off, how to choose our lambda, how it is behave between bias and variance situations. So just see, just let's see. So first I am saying decrease the, if we decrease the value of hyperparameter, then what happen? So if we simple see that if we decrease the value of hyperparameter, then what happen? Then error will decrease. So this is actually epsilon means what? Epsilon is the maximum value of our error term. So if we decrease the epsilon values, so our actual error are decreased, means errors are low on our training data set, on low. If our errors is low, this mean what? This mean our overfitting. We are going to overfit our model. Okay, we are just increasing the overfitting of our model. And suppose we are going to increase the value of epsilon. Then what happens? If we increase the value of epsilon, then we are going to increase the value of error terms. This terms is increased, error is increased, means we are simply add the errors in our training data. Actually we are going to add the errors in the training data. Means what? This implies that our tendency to make our model underfitting will increase. We are increased our underfit model. Our tendency to make our model is underfitting, it's increased. So simply, I think now you understand how the value of the parameters was important. So how to choose the proper epsilon for this kind of SVM regressor technique. Now let's see one kind of data set. Before just I'm going to discuss. Suppose let's say this is on our axis, and it will be better if it. Okay, suppose it is our independent axis, and it is our dependent axis. It's called y. Lie in this yi hat lies in this direction. Yi, so simple, not yi hat, yi. Just to plot our data set, and here it is our x. Suppose let's take our data will be like this. Suppose like let's take. Just see, I'm going to change the color. I'm here using this one. Just see the blue ink. Just I am taking this data set. So pictorially I going to see the how this one import this area, this one. So from the data set, if you see, this is the, it is not possible to separate linearly. It is simple and non-linear data set. Okay. So if we just see in geometrically, what will be the best regression line of this data set? So I think the biggest regression line of this data set will be like this. So let's take this one is the best regression line. Suppose let's take this kind of data, this kind of. So this is the our best regression line. Okay, if we just want to just we are using this model. Just if we consider this model, that is kernel SVR plus hyperparameter theorem. So this will be the our, according to our model, this will be our best regression line. Now just if you see, suppose let's take one, I'm just going to draw one thing. Just suppose let's take our original true regression line will be this one. Suppose let's take our true regression line will be this one. Just see the white. Okay, suppose this one is the true regression line. True regression line, and suppose this y our is the approximate regression line. Approximate regression line. Oh, okay, this is our actually true regression line, and this is suppose for some data set this is our approximate data set. But we are interested to find this kind of curve. Actually, for our real curve, we are interested. So if we choose just simple, if we choose the epsilon, if we choose, suppose epsilon, we are choosing so small value, suppose 0.001, we are choosing the epsilon this value. So in such situations, suppose write down, suppose I am taking epsilon, I am choosing the epsilon 0.001. So in such situations, we will see that our regression line will be like this kind of this. When our data set happen, then we can easily trace our original true value data set. Okay, it approximately equal of this. But when our data are ending, then it will behave suppose like this. Suppose like this it is behaved. But in actually originally our data will be like here in this region. It will be original data will be this kind of pattern it will taken. But when our data is, number of data sets are end, number of data is end. So in such situations, this regression line, that is rate 1, will misbehave. Okay, actually it is not to find the proper kind of thing. So in such situation it will be misclassified. In such situations our data set is misclassified. So these situations we call that overfit situation. In such situation we call it is our actually overfit situation, because when we have our data sets on that time we can easily find our error is absolutely, model is absolutely okay. But when our data is something we are just moving our data, then our model just behave like unacceptably behave our model. Okay, so in such situations we are getting just overfit model. Now let's consider another. Suppose I am taking the green one. Suppose let's take our, now we are choosing epsilon is equals to 2. Okay, suppose let's take we are choosing epsilon is equals to 2, that is large value. So in such situations we get the data will be, we get the approximate line will be like this. It is approximate, it is near about the linear line, approximately linear line, means it is just don't care about the misbehave point. We are here actually we are don't care about our point. how pointer classified. So in such situations, this is, if we choosing this one is the underfit. This is actually your underfit graph, and this one rate one, this rate one is your overfit, and these are underfit graph. Okay, so we see that both the situations we have to handle the situations both for lower value of epsilon as well as for higher value of epsilon. We have to handle the situations. So overfit model is not as good, and also underfit model is not good. So we have to maintain the things between them. It is the underfit situation. So we have to choose the value between we have to choose the value between underfit and overfit. We have to choose the value between them. So this is the job of our hyperparameter table. We have to choose the upper value between them that will fulfill our requirement. Yes, this is the actual thing, nothing else. So according to our requirement, we have to choose which kernel, which hyperparameter, and which equations we have to choose. So the example from this lecture, we have seen that. So the regression is nothing but simple modifications of the classification technique. Then we can easily build the regressions of SVM. So okay, so this lecture all about that.